Here's another example where we look at critical path analysis and activity float time. So here's an interesting network here. It's just a sort of a random directed network that represents a project of sorts, I guess. And now I've already done the forward scanning. Okay, so these are the numbers in black, and the backward scanning are the numbers in green. So you may want to check that for yourself. If you recall with forward scanning, we check basically with vertices where there's multiple ways of getting to a vertex, we need to put the highest number, okay, when you add up the weight of the edges that make up the path. So for example, to get to this vertex here, we can go via A and D, okay? We can go via B direct, or we can go via C and E. So C plus E, so that's 3 plus 5, okay, gives you 8, which is definitely the higher of the three possible ways of getting to this vertex. And likewise with backward scanning, so going back against the flow, the flow of the arrows there, if there's multiple ways of getting to a vertex, again, the lower of the three numbers is what we put here. And so these are the numbers in green. Okay, so for example, we got this entire project takes 53, let's say, hours. It takes 53 hours for this project. 53 minus 14 is 39. 53 minus 15 is 38. Okay, so notice these two numbers here are different. This is the earlier start EST and the LST. Okay, of the activity before it, but it can also mean that either of these two activities here could be delayed, in fact, depending on which one's delayed. So 26, that occurs because this one here, 39 minus 13 gives you 26, 38 minus 11 gives you 27, so 26 is the lower of the three numbers, okay, and so on. Now, to work out the critical path, okay, we look at the boxes, okay, where the top number and the bottom number are identical, okay. So obviously we have this vertex here is on the critical path. This one is on the critical path, so I'm just going to put a tick there. This one's on the critical path, okay. Notice that it's different here. This one's on the critical path because top and bottom boxes are the same. In other words, there's no slack time, okay. This one's on the critical path as well, and also this vertex is on the critical path, and of course the start is on the critical path. So drawing in the critical path then, so where I've ticked the vertices, okay, we can just draw in the critical path, okay. So I'm just going to draw it in green, okay. So like that, and up to this vertex there, and down to this vertex here. So there's the critical path there. Now, to work out activity float time, there's two ways of working this out. So I've decided, look, while there's two formulas, there's like a shorter formula and a more extended formula. It's the extended formula is actually the better one, okay? And so let's say we work out the float time for activity P, for example, okay? The way we work this out is we look at the two vertices, okay, that are on either side of P. Okay, you take the LST, okay, of the vertex after P, we subtract the activity time and then subtract the EST. Okay, so I might just do a few vertices here. So float time of P, okay. We take the LST, okay, which is 53, minus the activity time, minus the EST, which is 37. Okay, so think of it as almost like a sort of bottom box activity time, top box going backwards. Okay, so 53 minus 15 minus 37, if you were to work that out, should be 1, of course, and it is 1, and that makes sense. Okay, so the float time of P is 1. What about, say, M? Okay, so I might just raise it up a little bit. Actually, I'll just see if I can get a bit more of that board into the video. So, yeah, might be a little bit easier like this, actually. Yeah, that's good. Okay, so what about, say, activity M? What would be the float time for that? So again, activity M, okay, so okay, float time for M, we take the LST, okay, after M, so that's 38, minus the activity time, so 38 minus the activity time for M is 11, minus the EST, okay, so minus 11 minus 26, and float time for M is also 1, and that makes sense. Since this path, okay, MP, we have a float time of 1, that means M could be in fact delayed by 1 hour, or P could be delayed by 1 hour, but not both. That doesn't. We need to be very careful here that if we delay M by 1 hour, then P can't be delayed. Okay, so it really depends on when M starts as to when P can start. But if we start M immediately, then we have an hour. We can then start P. So P really depends on when M starts. Let's have a look at, say, another one. Let's say, for example, activity A. What would be the flight time for activity A? We take the LST. Okay, again, that's the latest start time for activity D. Okay, so the LST, though, which is at the end of A, minus the activity time. Okay, for A, which is 1, minus the EST, which is 0. So the earliest we could start A is actually right on the start of the project. So 4 minus 1 minus 0 is 3. Okay, so float time, okay, I might just write that here. So float time for A, okay, is equal to the LST, 4, later start time, minus the activity time, minus 0, and equals 3. Sorry, I had to sort of squeeze it up there in that top corner. And likewise for all the others, all the other activities, it can be worked out the same way. So just to sort of cut a long story short, and sorry that the video has actually gone this far. So just to summarize this, so if we have an activity, for example, okay, and there's some activity there, and okay, so let's call that the activity, for example, activity X, okay, and it takes, for example, a certain amount of time. So let's say it takes T hours, okay. We take, this is the LST here, okay, and this is the EST here. Okay, this is the LST of the activity that comes after activity X, okay. So the float time for X, okay, is given by the formula LST, okay. So this is the LST of the activity after X, okay. This LST here, this is why I've represented it diagrammatically, okay. This LST, okay, minus T minus the EST, okay, so that should be LST, actually that should be LST next, just to make sure I clarify that a little bit more, okay. We don't worry about this box here, we don't worry about this box here when we're working out the float time.